Okay, just want to continue our exploration of this system. So I've rewritten the equations for our system here. I put them in the most user-friendly form for finding partial derivatives. Here's the phase portrait that we managed to put together in the last couple of videos. And here's just a reminder of our equilibrium solutions. So what I want to do now is just linearize the system at each of these equilibrium solutions to see if we can't classify it. Okay. Now, I chose to just use the nullclines to get a sense of what the phase portrait looked like. Now I'm going to look at linearizing the system at each of the equilibrium points. If you're asked to do both, you can decide what order you want to do things in. Here, I'm kind of suspicious based on my phase portrait that 1, 2 is going to be a sink. Now, if I linearized the system first and I knew that it was a sink, that might help me in drawing the phase portrait because I know that near this point I had to be approaching that point. So you can sort of decide which you want to do first if you're asked to do all of these tasks. Okay. All right, so let's see. I want to remember that when I'm finding my linearized system, I switch to a U and a V. What that does is that just translates our equilibrium solution to put it at the origin, because linear systems always have the origin as an equilibrium solution and very rarely have other equilibrium solutions. And that's just going to be J times UV, where J is our Jacobian matrix. The formula for J is that we take the partial of f with respect to x, partial of f with respect to y. F here is the function that's giving me x prime. Of course, I'm going to evaluate these at the equilibrium solution. What I'm going to do is I'm just going to come up with a generic formula for J because we're going to use it 4 different times. It's going to be the same formula for calculating the matrix, but we'll get a different Jacobian matrix for each equilibrium point. My second row is then just the partials of G, which is the function that's giving me y prime with respect to x and then with respect to y. Okay. So if I take a look at what that is, okay, so here's f. Partial with respect to x is going to be 4 minus 4x minus y. Partial with respect to y is just going to be negative x. Here's g. Partial with respect to x is just negative y. Partial with respect to y is 3 minus 2y minus x. Okay, so that's a formula for my Jacobian matrix. So if I take a look at the Jacobian at the point 0, 3, and of course at the point 0, 3, my u and my v for this linearized system would simply become u is equal to x and v is equal to y minus 3. I just subtract the components of my equilibrium point. Okay. We don't actually need to write that out in order to be able to classify this, but the whole notion of linearization and switching to these new variables u and v is a little bit new still, so I thought I'd just remind us that that's what they'd be in this case. Okay, so the Jacobian at 0, 3 is going to be 4 minus 0 minus 3 is just 1. The opposite of x is 0. The opposite of y is negative 3. 3 minus 6 is negative 3 minus 0. So we get this. So our characteristic equation, I'm going to go ahead and just use the shortcut that it's going to be lambda minus the trace. Now the trace is negative 3 plus 1, so it's negative 2. So minus that is going to be plus 2 lambda plus the determinant, which would be negative 3 minus 0, is equal to 0. Now, that factors rather nicely. That's going to be lambda plus 3 times lambda minus 1 equals 0. So lambda is going to be 1 or negative 3. With 1 positive and 1 negative eigenvalue, I've got a saddle. And that's true in both the linearized system and the original system. Okay. I can sort of see that reflected here. Now, I haven't drawn anything to the left of this equilibrium solution because we were just working in the first quadrant. But you can see we've got one solution that's approaching, or actually 2 solutions that are approaching, but then over here, the solutions seem to be turning away. So it does sort of look like saddle-like behavior, that we're kind of coming in and then we veer away from that equilibrium solution. So nice to see that that's consistent. I don't think that really gained us any information that we didn't already have. Might have helped us if we'd known that before we started drawing the equilibrium solution. Again, whether you draw the phase portrait first or look at the linearization first, really just a matter of preference, although it's not necessary to do the linearization to draw the phase portrait, and it's not necessary to draw the phase portrait to do the linearization. So they're just things that kind of do complement each other if we want to do that. Okay, so let's take a look at our next equilibrium point. I think what I'm going to do, just to give myself a little bit more space, is write down this generic J up at the top of the board. So we really are just working with that here. And notice it wasn't necessary to draw the phase portrait for the linearized system in order to classify the equilibrium point as a saddle. Okay, so if I look at the Jacobian matrix at the point 1, 2, so that's going to become 4 minus 4 minus 2 is negative 2. The opposite of x is negative 1. The opposite of y is negative 2. 3 minus 4 is negative 1. Minus 1 is negative 2. Okay. So if I look at my characteristic equation, and again, I'm just taking the shortcut with using the trace and the determinant because I've been doing this a lot lately. I know that I don't trust myself to always remember that I've got to take the opposite of the trace. So if I haven't been doing it a lot, I would write out j minus lambda I. Okay. But here I can see my trace is negative 4. So minus the trace times lambda is going to be plus 4 lambda. My determinant is 4 minus 2, so plus 2. And the characteristic equation sets that equal to 0. So, using the quadratic formula, lambda is going to be the opposite of 4, plus or minus the square root of 16 minus 8 all over 2. So that's negative 4 plus or minus. This is the square root of 8, which is 2 root 2 all over 2. So that's going to be negative 2 plus or minus root 2. That makes sense. Okay, sorry. Having a moment there. Okay, so if I take a look at this, root 2 is smaller than 2. So negative 2 minus root 2 is clearly negative, but negative root 2 plus 2, root 2, is also negative. So both of these are less than 0. That means we're going to have a sink, and that's very consistent with the behavior that we saw in our phase portrait here, that we've got a sink at the point 1, 2. All right, so let's go ahead and work with our other equilibrium points. If I look at j at 0, 0. So x and y are both 0, so I'm just getting 4, 0, 0, 3. So I'm going to have lambda squared. The trace is 7, so minus 7 lambda. The determinant is 12 minus 0, so plus 12 is equal to 0. That's going to be lambda minus 4 times lambda minus 3 equals 0. So lambda is equal to 4, or lambda is equal to 3. Two positive eigenvalues, we've got a source. And that does look consistent here. We were moving away, and all of the other curves we got were moving away from the origin, because in region A we had to be going up and right, which is going to move us away from that origin. Excellent. So this one is a source. So let's just check 2, 0 very quickly. So that's going to become 4 minus 8 minus 0 is negative 4. Opposite of x is negative 2. Opposite of y is 0. 3 minus 0 minus x is going to give me a 1. Okay. So the determinant is lambda squared. My trace is negative 3. So minus the trace times lambda is going to be plus 3 lambda. The determinant is negative 4 minus 0, so minus 4. Oops, that should be a lambda squared. So let's see, that's a lambda plus 4 times a lambda minus 1 equals 0. Lambda is equal to negative 4 or 1. 1 positive, 1 negative eigenvalue, that's going to be a saddle. And again, we sort of see that. If I just look along the x-axis, it almost looks like it might be a sink, but along this line, we weren't coming down, which would bring us towards this. We were going up, which brings us away. So the curves sort of come in and then curve away, similar to what we see in a saddle. So kind of neat to see how all the pieces fit together.